To deploy autonomous AI agents, the industry standard relies on stateless, serverless environments like TypeScript. When an unpredictable large language model begins to hallucinate, it can trap these stateless functions in an infinite execution loop. Because the environment is stateless, these loops detach from the main thread, creating orphaned zombie processes that spin indefinitely alongside hundreds of overlapping race conditions. Every spin of that loop hits a paid API. Left unmonitored over a weekend, a single hallucinating agent can trigger tens of thousands of pulses, draining operating accounts before a human engineer even receives an alert. The solution requires migrating from these ephemeral serverless functions to a persistent, stateful Python runtime. By maintaining a durable process, we can apply thermodynamic limits, hard mathematical boundaries embedded directly into the software architecture to restrict the total compute energy a process can consume. Replacing prompt-based instructions with strict mathematical boundaries provides a structural safeguard for autonomous orchestration in production environments. The physical execution layer of this stateful architecture is built into a single Python file, engine.py. Delegating autonomy to an LLM inside a standard while-true loop is hazardous, because the loop relies on the AI's internal logic to return a resolution command. If the AI gets confused, the loop never closes. To bound this vulnerability, we apply a step-indexed logic framework. This illustrates a single loop track initialized with a maximum step index of 20. Every process spawned is born with a finite integer limit. Underneath, a system heartbeat pulses at a fixed interval, acting as the absolute clock. On every consecutive heartbeat, that central integer decrements by exactly 1 unit. Between each tick, the engine pauses to evaluate if the LLM is moving closer to the objective. If the LLM enters a hallucination loop and fails to resolve its task, the heartbeat continues until the integer hits 0, triggering an automatic hard kill switch. Trading infinite execution for strict time-bounded lifespans prevents catastrophic server lockups, completely protecting the underlying architecture, regardless of how deeply an LLM hallucinates. Before the engine allows an LLM to consume a step index, the request must pass through resourcegate.py, a thermodynamic checkpoint. This checkpoint evaluates the Gödel utility function, an algorithm that decides whether the system's actions are provably beneficial. The first variable is capital pressure. This tracks the accumulating API costs of the active agents, representing the exact dollar amount burned so far. This chart plots capital pressure on a rising red line against the second variable, user pressure, represented by the green line, which quantifies mathematical progress toward the goal. The governor continuously calculates the distance between these two vectors. The first hard limit enforcement rule projects the exact API cost of the very next LLM pulse before it executes. If that projected cost exceeds the absolute track budget, the governor triggers a kill sequence. The system also monitors for a margin zone scenario, where capital pressure rises rapidly but user pressure has flatlined. Instead of killing the process, the governor forcibly downgrades the request to a lower-tier, cheaper model. Rerouting to a flash tier artificially lowers the burn rate to preserve the utility ratio. This strict economic equation ensures the orchestration system only executes compute when it can mathematically calculate a proportional return on investment. When an operating model spins up multiple agents to explore a problem, the standard industry method for determining consensus is to prompt another LLM to act as a judge. This method adds latency and compounds API costs, while introducing a new risk of the judge itself hallucinating. We can bypass LLM judgment by applying the Cora model, a physics equation used to describe the phase synchronization of oscillators. First, the engine extracts raw semantic embeddings from the textual outputs of the multiple LLM agents, converting their words into dense numerical arrays. These multidimensional arrays are flattened and mapped as distinct phase angles on a complex unit circle. The system applies the Cora order parameter, denoted as R, to measure the average phase. When the agents reach consensus, the erratic points phase lock and converge into a single cluster, pushing the R value toward 1.0. If the agents are in a state of high entropy, outputting contradictory results, the points scatter widely across the circle, keeping the order parameter near 0. Translating textual semantics into precise phase geometry replaces the slow latency of LLM judgment with a direct mathematical calculation of true agent alignment. The step index, the capital governor, and the Cora models all integrate into a single interface, the Super Admin Governor dashboard. This dashboard tracks active processes in real time, displaying the current step index, capital pressure, and user pressure. As the orchestration loop runs, the blue step index timer depletes, while the red capital cost gauge simultaneously rises. If the live Godel utility score drops below the strict minimum requirement, the track reaches a threshold. The system responds immediately by killing the track mid-loop, halting all outgoing API calls. Terminating a process does not delete its data. The engine immediately triggers the refinery routing protocol. Under the principle that nothing is wasted, the refinery ingests the partial context and spent tokens back into the system's memory for future failure analysis. Bounding non-deterministic LLMs inside a persistent, mathematically strict Python architecture provides the predictability and auditability required for production